Okay, let's implement weight sum together. We first need to define the initializer as usual. And then we need to define forward. This one receives self HS and A. And then we need to implement backward. The initializer first, because this weight sum doesn't contain any learnable parameters. We're going to define self params and self grads as two empty lists like this. And we need a cache. And for forward, we get the shape first and extend A into the hidden state dimension like this. And you can explicitly repeat this process along the axis 1 like this. Either is okay. Now repeat H along the axis 2 like this. And then calculate T. And C becomes NP sum T axis 1. And in our cache, we store HS and AR, return C. This is our context vector. Okay. And then in the backward path, we retrieve the cached variables like this. Get the shape. And we make dt along this time dimension. And then we calculate DAR by calculating dt times HS, DHS, dt times AR, and dA becomes sum of DAR along axis 2. And we return DHS and dA. So this is pretty simple. So basically the same or similar computation flow. However, you need to think about the dimensions, which axis you need to repeat and which axis you need to sum up. And after that, we're going to implement attention. Using the two modules we implemented. We first need to define the initializer, self params, self grads, self attention, weight layer becomes attention weight we've just implemented. Attention weight sum layer is what we implemented as weight sum like this. And we're going to keep track of the attention we've calculated. The forward receives the list of encoder hidden states and the current hidden state of the decoder like this. And we calculate attention weight through attention weight layer. And we calculate the context vector by passing through HS and A. And store attention weight as attribute and return this context vector. And we need to implement the backward process, THS0 DA. Because HS goes through two layers, attention weight layer and attention sum layer. Therefore, we need to calculate two gradients for HS. with some layer backward. And then THS becomes THS0 plus THS1 because HS went through two paths, weight sum layer and then a tension weight layer. Therefore, we need to gather two upstream gradients for HS here and here and add them up. And return DHS and DH. All right, this is how we implement a tension. We modularize this attention weight calculation and weighted sum. And using these two modules, we implemented attention. And another thing we need is time attention. As we did for embedding, we extended embedding into time embedding and softmax with loss into time softmax with loss. And we need to also extend attention into time attention. So we need initializer. The initializers are quite easy because we don't have any learnable parameters. We're going to initialize them as empty lists. Forward, receive the hidden states from the encoder and hidden states from the decoder. Some of you might be curious that why do we need to receive the list of decoder hidden states? Don't we need to receive just one hidden state from the decoder? Actually, that is true when we are inferring. However, in the process of training, we know the ground truth. Therefore, we're going to feed all the ground truth outputs to the decoder. That is sometimes called teacher forcing. Because we do teacher forcing when training, we can get all the hidden states from the decoder. Okay? And you might remember that when we implemented sequence to sequence, the behavior between training stage and inference stage was quite different. Because of that, we implemented another method, generate. In this case, we get one output at a time and then feed that output into next time steps input. And we're going to do the same here. So in the training stage, we're going to receive the hidden states from the decoder at once. However, in the inferring stage, we're going to treat each output at a time, not at the same time, okay? So try to implement this time attention on your own and see you in the next video.